Good afternoon, everyone. I'm Titus Winters. I do not love doing my own introductions, but there's a couple things that I do want to say. I've been leading most of the C++ Common Library efforts at Google for 8 years now, dear Lord. I'm a maintainer for Google's C++ style guide. I founded Abseil. I'm now the chair for Library Evolution. That's the group at the standards committee level that does API design for the standard library. The new study group on tooling. I've done tons of guidance. I write a lot of the Tip of the Week series. I work professionally on providing good guidance on API design. And because of all of the code-base-wide refactoring work in Abseil and all of the other teams I've been on, we are subjected to the pain of fixing it when we get these things wrong. Which is to say, hopefully you can trust that I am not making all of this up. So, when we talk about design, why do we talk about design? I think we do this because we want to ensure that the things that we produce are usable, that people understand what you mean when you write out an interface, when you write out a function, when you write out a class, that they know how to use that. By looking at the things that work and the things that don't, we find ideas and design patterns that are easy to follow and that make the resulting APIs easier to work with. In the end, though, design serves us. This is largely not about math or fundamental principles of the universe. These are not rules, written out on stone tablets and brought down from on high. I am not bringing you commandments here. I am bringing you stories, best practices, things that I have found seem to be the way that we do things, things that I have found seem to be the right way to express things. But this is all going to be evolving over time, right? And I do want you to think about all of these things carefully. Don't just take my word for it. There are a few places where there are underlying maths or symbolic logic, and those things will help inform good design, and that'll be good. We'll sort of call that out. There is also this question. Are we prescriptivist or descriptivist? We can approach design just like grammar from either of these views. Do we see the rules as they were written down on those tablets and value the rules over all else? Or do we see that, oh, hey, we've made a mess, and some things work and some things don't, and try to produce rules that describe what things did and what things didn't, to encourage the good ones and nudge us away from the bad? And you can sort of take either viewpoint here, but I do sort of prefer when we approach things in a descriptivist fashion of this seems to work, this seems to not work, and here's why, right? It is really important to me that you all think about these things and understand why. This talk will be in roughly 3 parts, starting small with the basic units of design and working our way up to big questions like, is this an acceptable design pattern for types? There's a spectrum here. As we go forward in the talk, we'll go from talking about syntax to semantics to theory. This is scheduled in a 2-hour block here at CppCon, and I'm going to cover the first of these in this talk and the higher level pieces, types and type design, in the next slot. So we'll wade in, starting with the smaller and hopefully more easily understood part of the design spectrum. First, a question. What is the atom of C++ API design? That is, what is the fundamental small chunk of API design? It might not be the smallest chunk, but it should be the small thing that we reach for or that we think about most often. And if you asked me this a year ago, I would have said, well, it's the function, right? After all, that's the piece that we use the most, right? Free functions, member functions, special member functions, etc. But recently I've started to think, for maybe the last year or so, maybe functions are actually our protons. The better unit of design is slightly larger. The better unit of design is an overload set. When you have a well-designed, when you have a reasonable, when you have a good overload set, and it turns out there's actually very solid agreement amongst all of the experts on what is good and reasonable here. Overload sets are a much better unit of design, especially as we move to a richer type system, richer set of vocabulary types, concepts, and even deeper understanding of move semantics and move semantic designs. Pop quiz. What does this mean? What does a simple function signature like this mean? By the end of the talk, I want you to understand that this question is bogus. This question is ill-formed. You really need to know a bit more about foo, the type, and quite a bit more about f, and everything else that is named the same, everything else that is named f. I will say, if f is appearing all by itself and isn't part of an overload set, what we've got here is the function signature for maybe move. This nugget didn't actually fit anywhere else in the talk, and I really find it very important, so I'm just going to say that right now. You can repeat it 3 times to yourself under your breath. Right? It is maybe move when you see a function signature like this. Okay, overload sets. Somewhat formally, an overload set is a collection of functions in the same scope, its namespace, class, et cetera, of the same name, such that if any one of them is found by name resolution, they all will be. That captures the syntax, that captures what the compiler cares about, but not the semantics, that is what a user will care about, of a good overload set. The core guideline says very good things about this. Core guideline says 2 rules. What is overload options that are roughly equivalent? That is, if you have 2 things that are doing roughly the same thing, name them the same. And also the flip side, overload only for operations that are roughly equivalent. Right? That is, if you have 2 things that are doing something very, very different, please name them differently. Right? This should not be shocking. The Google C++ style guide says, use overloaded functions, including constructors, only if a reader looking at a call site can get a good idea of what is happening without having to first figure out exactly which overload is called. Right? You shouldn't need to do overload resolution in your head and know all of the symbols that might show up through transitive inclusion. Like, what's everything in your program that might have the same name? Right? You should actually only name things the same if it doesn't matter to the reader which of those is actually going to get picked. Right? It's going to do the same thing. We're definitely lacking a solid theoretical way to describe that same thing, because it's sort of squishy, right? Like, you can't really say, like, give me the semantic definition of, I have a function of 2 arguments and a function of 3 arguments, and they do the same thing. Like, that's going to be just weird to try to come up with any sort of formal definition of that, right? But we sort of can see what we mean with some examples here. So, for instance, we can overload on arity, how many parameters the function takes. And a great example of this is stircat from Abseil. We've had a variation on stircat in our code base at Google for many years. Pre-C++11, stircat was an overload set of something like 25 or 26 separate functions to go from arity 1 all the way up to arity 25. And it didn't matter, right? You don't need to know which of those you're calling, because what stircat does is take all of its things, convert them to string, and return you the concatenation there. And even after we switched to C++11 and moved this to being a variadic template, still doesn't matter. Right? It's one thing, because even that statement of it being a variadic template is slightly a lie, because the first, I think, 5 arities are hand-rolled free functions for optimization purposes to make it easier on the compiler, and none of that matters, right? Because you see a call to stircat, you don't have to count them, you don't have to know which one is called, it just does one thing, right? So you can clearly overload on arity in some cases like this. You can also overload on types, usually for types that are similar. And the most common example that you're going to find is for legacy, like string-ish overloads. There was some old function in your code base that accepted const char star, and someone got tired of that, and they added an overload for const string ref. And this is a great example of a well-designed overload set, right? You've got some sort of string-ish data. The user that is calling this function, or the reader of some code that is calling this function, this overload set, doesn't need to know which type is being passed exactly or which function is being called exactly, because we can see at a glance that the semantics are the same. Right? In this case, one is implemented inline in terms of the other. We see overloads throughout the standard library for optimization as a result of move semantics. For instance, there's vector pushback. This is an overload set. This fits and slightly expands our definition of these things have the same semantics, and I don't need to know which of these is called. At the call site, the user doesn't have to care whether it's the L value or R value version of pushback. At most, they need to watch out for use after move, but that's true irrespective of what API you're calling, right? You always need to watch out for use after move. This also helps flesh out what we mean by the same semantics. It is the same post condition on the vector, not necessarily for the t that was passed in. However, we don't actually really care about the post condition on the t because the t is either constref, not being changed, is a temporary, in which case we don't care, or was stood moved, and it's definitely not our problem. See previous result. Right? Is that all? Jibe? And it's also worth noting that the calling code, so long as it obeys this restriction, would be the same behavior, not the same optimization, if we removed the rvalue pushback overload. The semantics for all of our callers are totally the same, right? Nothing is actually going to change. So with those sort of examples, we can overload on arity, we can overload for optimization, we can overload for same types-ish, same Platonic notion of types, like string-ish data. Let's look at the overload set guidance. We can say properties of a good overload set. You can judge the correctness without having to do overload resolution. And I really like this second option here. A single good comment can describe the full set. For stircat, that comment would be something like, take all the provided arguments, convert them to string in the default fashion, and return a string formed by the concatenation of the stringified arguments. For the string thing, for foo, it'd be do x on the given string, whatever that is. For vector pushback, it would be something like add this t to the back of the vector. Right? We don't need to have a comment on every individual element of the set. Right? It's probably the case that one comment describing the overload set as a whole is actually more explanatory of what that overload set does. Right? And probably much clearer for a user. So this pushes some of the squishiness of what is a good overload set back a little bit onto what is a good comment, which is still squishy. I can't define it, but I know it what I'll see it sort of thing. But practically speaking, 9 times out of 10, you can spot the bad comments when the comment is encouraging you to do overload resolution. Right? Is that, like, you've all seen comments like that? That is definitely a code smell. Right? Does this all make some sense? Good overload set. Any questions? There are mics. Please feel free. I will not be able to see you, probably, but please feel free to chime in. I would love to hear from you. It's kind of awkward. When we start consciously treating overload sets as the basic unit of design, then we start seeing them in other places, right? The most important overload set of all is one that we've discussed a lot over the last few years, but usually not specifically in terms of it being an overload set. Any guesses? Copy versus move. I really, really like the formulation of copy and move as an overload set. This actually has huge conceptual ramifications when we reconceptualize along those lines. The type trait for movable isn't stupid anymore. It's always really bothered me that is move constructible didn't tell you whether it actually moved. It only told you if syntactically you could construct it from an R value. Right? That was like, yeah. Whereas now, when you recognize that move and copy are an overload set, all that actually matters is that you can construct from a temporary, you can construct from an R value, right? Because they're an overload set. Doesn't matter which one you pick. It is up to the type author in that model to ensure that move is efficient whenever it's plausible, right? It is up to the user to ensure that move is used wherever it's relevant or important. And the user doesn't need to know if a type has a move constructor, because you don't need to know which member of the overload set is chosen. This also requires that the semantics of copy versus move must be the same, at least with respect to the destination, the object being constructed. This matches the way that the standard library is behaving more and more. This matches the way that concepts for the standard library is being defined. This matches the behavior for papers that I've been writing about what the standard library promises. More on that later in the week. Move is an optimization of copy, is what I've been saying for a few years. But I think the better way to phrase it is move and copy must be a well-designed overload set. Does that make sense? Interesting. Explicitly conceptualizing everything, even constructors like move and copy, as an overload set gives us some guidance on things like explicit. When you view your constructors as an overload set, then you start having a better idea of when explicit applies. Does a user need to know which constructor was picked? If so, make that constructor explicit. Viewing it another way, copy and move are the canonical constructors that at least take parameters. We know their semantics. They take a t and they make a new t that's like the given t. That's the canonical constructor behavior. But if your constructor doesn't take t but takes some other type or maybe some other types, right? If you'd usually be comfortable passing t and u, foo and bar, const string ref and const char star as an overload set, then you're probably fine having constructors for both of those. Right? You could have a constructor that accepts bar in your foo, if it would be an acceptable overload set for both foo and bar. Right? And that's most commonly the case when t and u represent the same idea. Right? These are two different types of the same sort of canonical data. If it is, on the other hand, merely the case that we can construct a t from some bag of parameters, but those aren't basically a t. Right? This is vectors constructor that takes a t and a size. Right? That is not the same as a vector. That is a recipe for creating a vector. Then your constructor should be explicit. Right? Does that make sense? Any questions? Oh, wait just a second. I find that we wildly underuse explicit on constructors. And I think the standard library is as guilty as that as anybody. Like almost all constructors should probably have been tagged explicit. And we kind of screwed that up. But we're good? Okay. All of that said, in overloads, there's another really common pattern that I see, which is people attempting to use overload sets to enforce certain types of behavior. And my high-level guidance is don't use equals delete on a member of an overload set. Is that a question? Is that a question? Nope. All right. So I somewhat regularly see people try to delete a member of an overload set to enforce lifetime requirements. Show of hands, has anyone seen someone do this in their code? Yep, a few. Yep, looks like maybe 5% of you. The problem here is that no temporaries versus things that have the correct lifetime, things that have the lifetime that I actually require, are not actually synonyms, right? That Venn diagram overlaps a little bit, but is more disjoint than not. Like, generally speaking, if the lifetime requirement for a parameter to your function is not as long as this function call, like the default, simple, obvious thing, then it's going to be a little hard to pin down, right? It could be this function must live as long as this function, or this variable must live until the next time you call this function. This variable must live as long as this object. This variable must live until this thread completes. This variable must live until this callback fires, right? All of those things are complicated, certainly much more complicated than just no temporaries, right? Those are different levels of complexity. Starting asynchronous work is particularly challenging. And when you do this, the most common workaround for most people when they say, like, oh, geez, you've equals deleted this, I can't pass a temporary, I guess I'll make this not a temporary. 9 times out of 10, they do this by pulling out an automatic variable. And technically, now that's going to build. But the odds that the lifetime requirement of that automatic variable actually match the requirement of your kooky API are pretty slim. Right? In practice, your API that is kicking off async work or storing a reference, right, is going to require you to have a pretty detailed comment in its API saying exactly what the lifetime requirement on that reference is. The free-form nature, like the arbitrary, boundless possible complexity of that requirement is a whole lot more complicated than even C++'s type system, right? Equals deleting a thing here doesn't solve that problem. All of which to say, the solution to documenting lifetime requirements on borrowed references is either A, don't make it a borrowed reference, or B, document the actual requirement. The type system like this cannot do it for you. If you want to equals delete it on top of that documentation, I guess that's fine, but it's a half measure at best. It's a quarter measure at best, and it gets really messy, and it's misleading, and it's a false sense of security. And I would not accept it in code review, but I guess your mileage may vary. Good. Excuse me. There's also using equals delete or just eliding a function from an overload set in some cases in order to force the user to use the move version of a function instead of the copy version of a function. And in simple cases, maybe even in most cases, that looks fine. That could be fine. But in general, you don't know all of the ways that your API is going to be used. That is fundamental to the whole business of providing an API in the first place. While it might be the case that you know that many invocations of your function should be done via move, not copy, you can't know that for everything. Right? If I want to do 2 separate scans on a slightly modified chunk of DNA, it's less efficient to call this on temporaries because I have to do the modification twice. And if you make me contort my code so that I only do the modification once but can't call your move-only interface, I can do that, of course, but it is a little bit more awkward. My point being, for functions, you can't really know that nobody ever is going to need the copy API. And when you provide it as an option, the calling code is certainly simpler. Sort of at a very high level, don't be judgy, right? You don't know all of the ways that your code is going to be used. Be accepting. If you do somehow know that copies must never, ever happen, that is almost certainly a property of the type, not of the function that you're passing that data to. Right? Make a DNA class in this example. So if you're that worried about accidental copies adding up, make it a separate class. Don't use string, right? And then probably still make it copyable just with some special name, right? Maybe make it more explicit and hard to trigger accidentally. I've sort of snuck in here a pass-by-value design sync. Here, DNA scan is accepting a string, the DNA, which is presumably a very large string, by value. Ooh. Other things, like vector pushback from earlier, do this as an overload set. Which one is right? That is to say, is vectors pushback a well-designed overload set? Should everyone always be doing that when you're accepting a value to sync? Or is just accepting a value fine? And there's been a lot of discussion on this. In fact, I think one of Herb's keynotes the first year or two of this conference had a long section that was touching on a lot of the same things. There's been a lot of discussion and partial guidance on this, and a lot of that guidance does not agree, right? And to some extent, that is because there are a lot of possible questions, a lot of different scenarios that you might be optimizing for. So really, we should be asking some questions before we try to come up with perfect, all-encompassing guidance. And the questions that you might think, or that you might need to be asking, is this a generic, or am I syncing a particular type, right? In the DNA scan example, I'm syncing exactly string. That gives me some knowledge. Or I might be syncing exactly DNA strand, right? And that gives me knowledge about probably the relative costs of copying and moving versus what the function I'm about to do is. It's a question, although it might be good to, I can try to repeat, but either way. Can I clarify what I mean by sync? So there are a lot of functions where you pass a value in, and it's read and returned to you and nothing else, right? That's sort of normal. Then there's things like vector pushback, which is a sync. It's passed in and copied and stored, right? So for any function that you are accepting the input to then copy, either for storage in the very common case, usually like vector pushback, or even in some cases, I'm accepting it in order to make a copy that I'm going to mutate. You could imagine a silly function that is print everything capitalized, right? Which might accept a string and need to make a copy of it so that it can capitalize it before it prints it, right? So sometimes you might have either storage or I just need a copy. Does that capture it? Yeah. Yeah, and there's also the question of relating to whether it's generic or not. How expensive is the function compared to a copy or a move of that type or those types? Right? And if it's generic, like vector pushback, right, all you're actually doing is making a copy or doing a move. Right? There's basically no overhead above and beyond the cost of copy or move. For something like DNA scan, right, if I need to sync it, I'm probably also going to do a whole bunch of work on it. And that whole bunch of work is probably much more expensive than a move on a string or a move on a DNA snippet. Right? So you need to maybe weigh those things a little bit. But there are more questions. There's the question of, are there multiple parameters that are being sunk? Right? If I need to sync 2 or 3 or 4 parameters, then the cross product of const ref and ref ref for all of those parameters means I have a combinatorial explosion of elements in my overload set. And that just might not turn out to be fun. Certainly not fun to maintain. There's a question of, over time, as I maintain this library, as I maintain this code base, do I know that this is always going to be a sync of exactly t, or do I just want t-ish things? Right? In the case of accepting strings, you might, if you have a lot of not actually strings in your code base, but things that convert to string view, you might make your sync in terms of string view instead, so that there's one clear conversion point. And then there's the question, which I think Herb raised in his keynote a couple of years ago, of can allocation reuse dominate? And this is a case where if I have a type who has a member variable, like a log or something, then it could be the case that as I append data to that log, maybe it's a string, it may have to resize and reallocate as I append more data to it. And if I sync a new log, I sync a new string into place, the allocation of the old one is lost when I move the new one in. Right? And if I continue growing again, then I'm going to have to do all of that reallocation over and over again. That seems like a fairly rare case, but is not by any means unheard of. So it is actually a thing that you might actually have to consider, like when you're deciding how to accept your sync parameters. There may even be other questions above and beyond this 5, but I think that's a reasonably complete set and already very complicated. But I will throw out the following sort of very general guidance. I would probably personally provide this as the guidelines. You probably want the overload set of const ref and ref ref if the implementation of your function is small compared to move constructing a t. It is a little bit more complex. It is worse error messages. It is worse compilation performance. And it is probably too much of a pain if you have multiple parameters. Right? There's that combinatorial explosion. You could sync by value if the implementation is largely larger cost than move constructing a t. Like in the DNA scan example, I'm about to walk through everything in a DNA snippet. Right? That is bonkers more expensive than moving a string. But it does also constrain you a little bit. You want that to continue to be a t and exactly a t for all time. You don't want conversions in there. And then there's const tref is actually never a terrible choice if you don't know the answers to these questions, because it's simple and it gives you flexibility. It's well understood, right? It's hard to get wrong. That's how I would simplify that. It's also worth noting that this gets a little more complicated if you're dealing with strong exception types and syncs that may throw. If DNA scan may throw and DNA needs to be strong exception safe, then you have an additional set of constraints. Practically speaking, syncs don't usually throw except for allocation. If exception safety is your primary concern, you may have to reevaluate this a little bit. Mostly don't pass by value for types that are strong exception safe. When I'm talking about non-sync overloads, historically I find that we're talking about const char star and const string ref. I mentioned that a little bit. these tend to have a similar look. In modern code, we tend to replace that overload set with string view. And once we start talking about string view as the string-like parameter type, then we start looking at other common non-owning parameter types like span. These have unusual designs. There are sharp edges. There was a whole talk on that already this morning. Span even leads us to a bigger can of worms because unlike string view, like string view does one thing, it is character data. Span tries to be a general, any contiguous range of type T, but there are lots of contiguous ranges of almost T that you're reasonably likely to work with. For instance, there's pointers versus smart pointers. We can easily publish guidance to say, don't pass smart pointers by constref in general. If you want to pass a pointer, pass the pointer, not the ownership wrapping information. So we get it ingrained, don't do this, like identify this in code review, suggest const t star or even const t ref. But types don't actually decompose, right? A vector of unique pointer t is not convertible to a vector of t star. And if you've got a vector of owned pointers and need to invoke a function with a vector of t star, there just isn't a good way to do that. So modeling based on span, it is not hard to imagine producing a more generic span of t-ish things. I've seen this in my code base as any span, which I don't love the name, but I do increasingly like the type. It effectively type erases a contiguous container of things that can be converted to t star or t ref in a fairly clear fashion. And we can go further and further down that rabbit hole. Maybe it doesn't need to be contiguous. Maybe it's just some form of range. Maybe we can do this for associative containers, and we have a map view or a set view. Stepping back a little bit, C++ is a language that is all about types, more so than basically anything else. Overloads for non-owning reference parameters, like string view and span and any span, are about getting closer to duck typing in terms of what types are accepted, which give me anything that looks like a duck and quacks like a duck, and I will use it as a duck. Bjarne was talking about this in the keynote this morning with concepts. It's a language approach to a very similar problem. And those are the two main conventions that are emerging in this space, right? We can, in the library, build non-owning reference parameter types like these, or we move to more generic code and use concepts. And when it comes to that question of which of these will emerge, I don't think the community has enough experience to provide particularly deep guidance yet. My suspicion is that this will come down to whether the library of types like string view and span are found to be sufficiently expressive. If the library providers of the world build a rich set of such types, we'll probably go that way. This approach has a head start, after all. If we invest a similar effort in concepts and, important, we find only a comparable set of sharp edges for concept usage versus view usage, then it may be that concepts comes to dominate. That is a pretty significant shift, and with a lot of unknowns. And it's unclear yet whether everyday programmers can write in a generic and duck-typed fashion efficiently and safely. We will see how that turns out. But interestingly, we already have a trial of that happening right now without concepts in the form of callables, std function. Even without concepts, we can write fairly reasonably something that takes in a callable in either a library or a language fashion. Both of these have their uses, but I think when we're writing everyday code, most of us are going to reach for the library form, and that seems telling. Until we have erasure and storage for concepts, I think we're probably going to reach for the library solution. If I had to guess about the future, I'm going to guess that we'll devote a fair amount of energy to both approaches, and we'll wind up with a powerful, very useful set of concepts, and then those will be type erased and provided as library, like with library types that wrap them. And most user code will deal in those library types. It's just a guess. Even still, std function is a little unusual in this class of type erased parameter type. Because when we compare to string view or other view types, std function is simpler in a couple of very important ways. First, it's only erasing one thing, right? If I accept a std function, I'm accepting one callable thing. Nearly every other commonly discussed type erased type is erasing a collection of things. String view and span erase contiguous sequences. Any span erases a contiguous sequence of not quite T. Map view or set view erase the ordering details of some associative container, et cetera, et cetera. When you're type erasing a single thing, it is much easier, as std function does, to make that an owning type, a type where you can copy it and not have any requirement that the original outlive the copy. When we do type erasure over a container, on the other hand, over a collection, then we generally don't want to actually copy all of the things in that container. And we rapidly wind up with types that are very, very easy to make them dangle. And then we get two big schools of thought. We can have non-owning reference parameter types only as parameters, right? Have string view only as a parameter type, never use it anywhere else. And this school of thought will say non-owning reference parameter types are okay, as long as they're only function parameters. And then there's the use with caution school of use non-owning reference parameter types, just carefully, like, yep, there's sharp edges there, just stay away from the pointy bits. Always question storage of any such type. There is also a third school of thought that these types are all completely garbage and too hard to use and we should throw it away entirely. I don't see that happening, but I have been surprised before. Even with just these two options, we have, as a community, a difficult choice to make, especially in a language with such lofty goals as do not pay for what you do not use. Because there are absolutely use cases for non-owning types like string view above and beyond just as a parameter. Consider file name processing. You could imagine a path processing function that takes a string view for the path and returns a view into it for the suffix or the file name or the directory. But note that we're looking at this. Using string view on input here means that we don't have to overload on char star and string ref and whatever user provided types might be contiguous and useful. String view does all of that overload work for us. That's the point of vocabulary types. That non-owning parameter type as a replacement for an overload set is very powerful, and it is why we are talking about this right now. We could make this design a little bit more palatable to some people by changing that return value to string instead of string view, but forcing a copy there and changing that return type feels a little awkward, especially if this wasn't suffix but was directory, right? If you deal in very long file names, those might start to actually be large copies. That might start to add up. Don't pay for what you don't use. That's C++. Right? If you can use this style of design safely, that sounds like a very C++ thing. But it is awfully easy to misuse. Take a glance at this slide. Half of these are bugs. And they are awfully close neighbors to code that works just fine. All of which is to say, if we continue to build views and other non-owning reference parameters, there's going to be a tension here. I think that the basic language, like design and evolution principles, are going to say, yes, it's fine to use these carefully. If a user hurts themselves on that sharp edge, that's on them. But we're definitely going to see a lot of very caring people offering guidance like, never use these except as a parameter, or even never use these at all. And that is a hard tension with, these are going to be the most efficient ways to express that overload set, for instance. Personally, I've been using string view for quite a while, and I find it pretty easy to spot questionable use in code review. Anytime that it is used as anything other than a parameter, I ask, why do we know that the underlying data will live longer than this view? That does not work so great if you are an almost always auto person, sorry. But this is all sort of a long tangent on doing type erasure for parameter types and duck typing in a library form. There's open questions here. We'll see how this all plays out. But we need to pop back the stack a little bit. We're done looking at overloading on parameters or producing parameter types that hide that overload set for you. And instead, we're going to look at the other important dimension for overload sets, which is method qualifiers. This is a really important variation on overloads. You can overload member functions based on method qualifiers, either ref qualified or const qualified. Overloads that vary in const qualification tend to be of the form, access this underlying data in a const appropriate fashion, right? You see this in vectors, operator, square brackets, right? If you have a const vector, you get a const tref. If you have a non-const vector, you get a non-const tref. Right? Simple, easy, obvious overload set. Overloads that vary on ref qualification tend to be about optimization. You can do one thing safely, the L value qualified version, and if we know that we are operating on a temporary or operating on an R value, we can more aggressively optimize by leaving the object as a whole in that dreaded valid but unspecified state. So for example, in C++20, the string buff type will gain an overload for stir, a ref qualified overload for stir. Here, a ref qualified overload means steal. So you can change your code that is returning buff.stir, which has to copy out of the buffer, to return stood move of buff.stir, to say, I'm done with this buffer. And because I'm done with this buffer, you don't have to copy that string out. You can move that string out. When we use a pattern like this, we don't need to worry about scary naming for destructive member operations. With just consistency with higher level rules, don't operate on moved from objects, does all of the warning that we need to do. Right? That's very handy, like you rely on existing user experience and understanding. And forming these performance when available overload sets is also a nice way to be future compatible. We can all start writing this return statement right now. It doesn't hurt anything, and it expresses a reasonable intent. I'm done with this buffer. When the underlying standard library catches up, it'll just optimize a little better, right? It's a future compatible design. That's always nice to see. When we combine const and reference qualifier overloads, we can keep const correctness and provide good optimization, like in the case of optionals value. These types of overload sets still meet our general definition for good overload set. A user does not need to know which one is called. A single comment can describe, probably more clearly, the behavior of the whole overload set without having comments for each member individually. While we're here, we should talk a little bit about method qualifiers on their own without the aid of an overload set. So what do ref qualified methods mean when not part of an overload set, and what do const methods mean? If you've got nothing but an rvalue-ref qualified function, that means do once. This is a great design for destructive operations and things like call this function at most once. It should only be used, however, when the L value equivalent semantic would be buggy or break the design of your type, not just because of inefficiency. Right? This goes back to the don't equals delete things just because you're being judgy. Right? It's perfectly reasonable for me to provide only the R value version here because the whole type is this is a one-time callable. On the flip side, L value qualifying a function says don't do this on temporaries. This comes up almost never outside of overload sets. But it does have one case that I've been seeing, which is we should maybe be L value qualifying our assignment operators in general, right? Like you can currently assign to a temporary of most user-defined types. You currently cannot assign to a temporary of an int. Like we are not doing as ints do. But if you ref qualify it like this, then the compiler will catch that that assignment is probably nonsense and not what you meant. In practice, I don't think I've ever actually encountered that bug in real code. I don't actually care that much, but from a design consistency perspective, that's maybe an actual use case, and it sort of expresses what the intent is. Moving away from references, what do we really mean when we const qualify a thing? Hypothetically, if we marked every method as const and every member as mutable, this class builds just fine. But this is going to be an absolutely rotten type to work with. Const should mean const. But there are types that have mutable members, and those aren't actually a problem. But there's some question, there's some connection there. How do we use const and mutable well in design? And I suspect that there are a couple ways to view this, but the one that has given me the most mileage is the tie between const methods, mutable members, and thread safety. The standard has some things to say about this. It says it in a very obtuse fashion. I'm 95% sure that's the right citation. If you squint, it talks about read access, write access, modification, and const arguments. According to the person that claims responsibility for that wording, it's horrible wording, but the intent is roughly this. Const accesses to standard types do not cause data races. Standard types are thread compatible unless otherwise specified. Here we have to define thread compatible as a very hand-wavy definition. Concurrent invocation of const methods on this type do not cause data races. Any mutations of an instance of this type means that all accesses require external synchronization, as opposed to thread safe, where concurrent invocations of const or non-const methods do not cause data races. That's mostly things like mutex. There is, of course, also a thread unsafe classification, but you should just not do that. More on that in the next talk. It's interesting to note that if you build your types out of thread compatible or thread safe types, and you don't use the mutable keyword for your member variables, then you're probably thread compatible right out of the box. There are some scenarios where pointers are shared around and that isn't quite true, but more on that in the next talk. In this model of things, const is less about I'm changing the internal values and more about it is safe to call this method concurrently. And with that model of things, we can see at a glance that this class is thread unsafe unless response is inherently thread safe. And usually what such a design requires is a mutex. But what just happened? We started talking about properties of types, which means that we're finally ready to move on from low-level API design and talk about higher-level stuff. But it is also important to note that this is a bridge. There's a bridge between these domains. Const is both a promise about your values and a promise about the ways that it is safe for your type to interact with the rest of a program. And that makes that a topic for the next talk. And we have lots of time for questions. And I will leave this up to jog your memory. There are microphones in both places.
So you were talking about the qualifiers on methods. I'm not sure I understand the meaning of a const rvalue-reference type method.
Yes. The optional value overload set has a const ref in its overload set. And I'm 95% sure that that is only there so that it works nicely in generic contexts. But like semantically, it doesn't mean anything.
Okay, so I'm not crazy.
Yeah, you're
sounds
not crazy.
meaningless.
Yeah, it is. The first time that I took a good hard look at it, I'm like, wait, what? Huh? Yeah, you're well spotted. Yeah.
Kind of in the same vein with ref qualified members, you talked about the stir member of string buff, but and you talked about how it interacted with the guidance that we not use moved from objects. Now imagine that we had a type that was like string buff but had separate buffers for input and output, and had ref qualified members that allowed us to retrieve either of those. If we followed the guidance not to use move from members and ref qualified them both, we could extract one or the other, but not both in a destructive manner. What are your thoughts on that kind of API design where a type is safe to be used after it's moved from so that you can extract other members from it destructively?
I think it would be really hard to express the, I think it would be really difficult for that to actually play out in practice because the move constructor, no, that's not quite right. I would be deeply skeptical to start with because like the very, very high level principle is don't touch it after you've called std move on it, right? Except in very, very unusual circumstances that you do not want to get into. And so I think you would probably be better off with some other naming for those types of things. And I haven't actually seen a whole lot of value types where there's multiple like logical parts to it that you would want to be consuming. I think perhaps a more accurate thing would be that you wanted an accessor for the input and the output individually that you could steal from. And then it would be a std move on that member, but you'd have to sort of make that member public. And I don't know. It's going to be kind of a weird type.
Thank you.
Yeah.
Actually, in the same vein of move from types, but I guess you're saying that the advice is to never touch a move from object. There are cases definitely with the standard library objects where you potentially could reuse them with certain constraints, like if you build up a vector that's a member, and once it's built up to a certain point, you can move out those values, but then start building up your vector fresh again, as opposed to having a unique pointer to it. I mean, do you see the standard keeping that kind of generic advice, or do you see certain standard types providing slightly stronger guarantees about what you can do with move from objects?
I mean, you will always be able to, in the next talk, we will talk a lot about the precondition, like preconditions expressed on the APIs of a type. And you will always be able to call any function that has no precondition after it has been moved from. Whether you should is an entirely different story, right? It is definitely well understood that when you move from a unique pointer, now it is definitely null. And so you could call reset on it. When you move from a vector, you don't know what's in it anymore. And
or
we
assign
all
to it or something.
Right. You could assign to it. You could call clear on it. Right. You could ask it its size, right? But you should not make any assumptions about data being there or not. Right. But practically speaking, the likelihood of encountering a scenario where the clearest way to write your code actually has you reusing that zombie husk seems rare, right? And you're probably better off not causing the, wait, what? Of you're reusing it after move. Like, just don't poke that bear. Like,
I have
yeah.
a personal example, which I'll talk about later.
Yeah, I mean, like, yes, technically speaking, it will work. But there is a higher level requirement on everyone of don't produce code that makes your reader go, what? Because confusion costs more than CPU cycles. Right. Over here.
Wouldn't you mind to show again the slide with the results of function returning string view, taking the string view and returning part of it? Yeah, the one with like red and yeah, it's beautiful. I'm afraid it's not very safe. I mean, you marked option 4 as good. And I believe it's undefined behavior.
No.
Your argument will be destroyed.
So
your
no.
String actually won't.
Temporaries are destroyed at semicolons. By the time the string's copy constructor runs, actually, by the time the string's, yes, copy constructor, move constructor? Copy constructor. By the time the copy constructor runs, the temporary is still there because the temporary doesn't go away until the semicolon. Like, I guarantee this is fine. John.
Hey, Titus.
What's up?
So you were talking in the beginning about how overload sets should define a group of functions that are all semantically basically the same.
Yep.
And you were also talking about 5 minutes ago about how it's really important for const to be meaningful, especially in thread safety situations.
Yep.
And there are pretty commonly used overload sets, like operator brackets is like this, which often will overload on constness, even though giving a read-only reference and giving a mutable reference are really, really different, especially in a thread safety context. But I don't think anyone in the room would argue that that like operator brackets is somehow completely a broken design, like on a vector or something. So how would that fit into the advice that you're giving us?
Well, so the advice is, like, at a very high level, the advice is, it is probably a good overload set if you can have a single comment for it, right? And the comment for that const, non-const overload set on vector is give me the specified t, right? Like,
Sure.
Give me that object, maintaining as much constness as you can if you want to be really wordy about it, right? But, like, that is a reasonable definition.
Awesome.
Yeah.
Thanks.
Yeah. And yes, I will pitch Jeff Romer's talk on thread compatibility and thread safety on Thursday. That's actually in my script in the next part of the talk as well. So everyone that sees both of these will get that pitch twice. But yes, go to Gromer's talk. It'll be great.
I'm not going to try to start a debate, I suppose, on edge cases, but I do have some curiosities regarding perhaps some guidance you might offer on how access modifiers, when used with different types of constructors, and more importantly, non-const references, when passed to functions, how would you recommend this mechanism as a tool to prevent implicit conversion from types, particularly in my example, I suppose, const char star to standard strings, but plenty of times where that has come up in other situations.
I think that actually is the third bullet point here. Make explicit any of your constructors that aren't an obvious, easy overload. Like, I think knowing what we know today, we probably would have made the const char star constructor for string explicit so that you can spot the fact that, oh, that is an expensive copy.
Sure. You would encounter the same scenario with assignment operations as well when you're not dealing with a constructor at that particular point as well, but you'd still end up having to encounter implicit conversion for the type provided.
I think I lost you. Sorry.
I may just be blowing hot air, I suppose.
No, like, it is, code is very hard, and it is much easier with examples instead of
Sure.
verbally. So come find me afterwards if you want to talk. I'm happy to. Yeah, I just can't quite do that one live.
You had a slide about taking param data as sinks.
Yep.
And about taking it as value versus ref versus
Yep.
rvalue-ref. And the guidance was based on sort of a relatively complicated evaluation of whether one operation is going to be more expensive than another. Is
Yep.
there a fundamental reason why that's a decision that I have to be making as an API designer and the compiler can't decide it for me?
In this language, the compiler can't design for you. We have too much legacy stuff that we can't change these behaviors. I think in theory, it is the sort of thing that might be amenable to optimization or to automation, but that would be a mad science project first off, in order to figure that out a little bit, because among other things, it's going to change wildly if you take a mutex. It's going to change wildly if you call an RPC, right? Like when you're syncing a thing, you need to know the cost of those things, and not every line of code is equivalently costly. And trying to teach the compiler, which of these things is expensive, that would be a neat trick. So in the presence of magic, yes, in theory, that would be cool. And until then, it's going to be a little complicated, and I don't know. Use your best judgment. It's hard. So.
Hello.
Hey.
In a very early slide, you had sort of the general idea of with an overload set, if you're taking in a std string and then it's a lightweight wrapper around something that goes to a const char, pointer to a const char, that was a good thing. And then I think at a later point, if I understood you correctly, you started saying that when you identify people using const references to std unique pointers, in code reviews, you see that as an issue.
Oh yeah.
Is it kind of like an issue, and it's just a nice wrapper around passing a pointer down to some?
It's not a wrapper around a pointer, right?
No. I mean when you make add something to your overload set just to make it easier for people already using unique pointers to pass down the raw pointer.
No, because the operation to actually extract a raw pointer from a unique pointer is O1. Whereas if you only had a const char star overload, no. Yeah, now I see your point. There is a logical inconsistency there. I think it is that it is very common for us in legacy code bases to have char stars floating around and strings floating around, and it's nice if you don't have to know which one it is and which one to care about. Whereas passing a unique pointer by reference, especially by const reference, is just fundamentally a little silly, because you're saying, I can only invoke this if I already have ownership of the thing, but I'm not transferring ownership, right? It'd be like, that would be an okay function by itself if you had to prove ownership of an object, which is a weird semantic. I guess, strictly speaking, if it is an overload of t star and const unique pointer ref, I guess, strictly speaking, that might be okay, but I don't know. That's a weird, like, I feel like that's the wrong result, but I think you might be right. So, yeah, I don't know. I have to think about it, but interesting, yeah. We are strictly out of time, but I will take Eric.
Hi.
What's up?
So Titus, I think I heard you suggest that you recommend explicit on constructors of more than one argument.
If those constructors aren't logically the thing, like for any constructor that is accepting a bag of parameters from which you can construct, as opposed to the parameters it has are platonically like the same notion as what you are constructing. So maybe in a ranges form, 2 iterators is a range, right? But in a vector, a t and a size is not actually a vector. Did I head you off?
No, I mean, it's a question I've
Yeah.
had, because I mean, C++ has this language feature, and I've never known what to do with it.
Yeah, I think by default, we should be tagging all of the constructors explicit until you think about it. And we have the default wrong, as is often the case. But yeah, like I really think that explicit should be way more common. There's a tip of the week on that.
Okay, thanks.
So, yep. And we're out of time. Thank you all very much. And